All right, so today we're going to take a look at section 2.5, which is called implicit differentiation. Now, what we've been working with so far is differentiation, but specifically we've been working with something called explicit differentiation. So when we do explicit differentiation, we are able to have y on one side and the other side has all my x's on it, okay? And, or if it's not like that, it could be simplified to be that way. And then this is exactly what we've been doing, okay? So this is just sort of a formalized paragraph, I guess, if you will, a couple sentences, whatever, about what we've already done. So what we're doing today is called implicit differentiation. So when we work with implicit differentiation, we're taking a derivative y in terms of x when an equation either cannot be simplified to say y equals, or maybe it's just absolutely atrocious if we did it. In order to use this method, we treat x and y as variables, and then we use the derivative rules that we've already learned. There is one caveat at the end, is that we do have to solve, right? The final answer has to say dy dx equals. Now, this is not notation that I've used a lot, but dy dx is the same as saying y prime. So we always have our answer that way when we're working with derivatives that are explicit. Everything you just did on the gateway, you found out y prime equals, right? Well, sometimes it doesn't actually work out to having it as dy dx or y prime equals the rest of it inside of implicit differentiation, and I'll show you what I mean. So we're going to take a look at a couple of examples. This is an example where we actually could solve it for y. We could, right? We'd have to move the x squared to the other side. We'd have to multiply or divide by -1. We'd have to take a square root, and when we did so, we would put a plus or a minus on it, right? So when we do that, it would end up looking kind of atrocious. It wouldn't look good, and we'd have to end up having a plus or minus. We'd have to have a chain rule involved. It'd be a mess. Well, the cool thing is that with implicit differentiation, it's actually very clean. So let me show you what I mean. You've got x squared. You know the derivative of x squared. What is it? 2x. Fantastic. There's a 2x. Okay, so now x is a variable, y is also a variable. Okay, so y squared, what's the derivative of y squared? What do you think? What's that? 2y, right. So there's just a negative and then there's just 2y. But here's the kicker. Y is like a function of x. At least it is if we're a little bit careful on rewriting this thing. We can write it that way. So y is a variable defined in terms of x. So anytime you take the derivative of y, which we are, right, y squared is 2y, it's like working with the chain rule. So remember the chain rule says take the derivative of the outside. Okay, so the squared comes down and I decrease the power by 1. And then I need the derivative of y. Well, the derivative of y is y prime, right? Normally we have it written y equals, and you take the derivative and you write y prime equals all that stuff, right? That's the way it normally looks. Agreed? So the derivative of y itself is y prime, or for the purposes of what we're doing here, it's a lot easier notationally in the end for us to just write it as dy dx. So remind yourself, dy dx just means y prime. One of the things that's nice about the dy dx notation is it's a little bit more intuitive of what we've actually found. Remember, we're finding slopes, right? So y prime is actually a slope. And a slope is a change in y over a change in x. And do you see how it looks like that? dy, the change in y, over dx. So in sort of intuitively, it's a little bit more clear as to what we're finding. We're finding a slope. Now here's what's left. We've got equals 25. So what is the derivative of 25? 0. So this is actually really clean derivatives. I mean, we just have power rules, right? X squared, 2x, y squared, 2y, dy dx. It was very clean. Let me go back and remind you, if we actually solved this for y, we'd have a plus or minus, and we'd have a square root, and we'd have something underneath the square root, so we'd end up involving the chain rule. It'd be really messy. Okay? Now, the one caveat at the end that I mentioned over here is that we need to solve it for dy dx. And you can see right now that it isn't solved for dy dx. The dy dx is intermixed with other pieces of information. So I need to isolate dy dx. I need to solve for dy dx at the very end of the problem. So part of that's not too bad, right? I'm going to move my 2x to the other side. So I have negative 2y dy dx equals negative 2x. And then, what do you suppose we'll do? Trying to get dy dx alone. Yeah, what was that, Hayden? Yeah, we'll just divide by negative 2y. So dy dx equals x over y, actually. Right? Because it reduces. So you might be looking at that and saying, okay, but that doesn't look like what I would get if I took the derivative with explicit differentiation, right? If I moved my x to the other side and I took my square root, I had the plus or minus, and then I did the chain rule. And you're right, it doesn't. But the reality is that on these, we get to leave the y on the right-hand side. We're not trying to sort of plug in what y equals or anything like that. We get to leave it there. And that's what makes implicit differentiation kind of nice. Now, the thing that makes it maybe not quite so nice is that while I could have done this one explicitly and it would have been a mess, there are other problems like the next one. I couldn't even do it explicitly. There is not a way to solve this for y. There's just not. So implicit differentiation sort of opens the door to things that are messier as well, right? Because now I can find a derivative of this even though I can't solve it for y. Now, there's a couple of different things that you could do. You could take the derivative the way it is right now, right? So you'd have a quotient rule on the left, agreed? Yeah, you could do that. It wouldn't be wrong. But you know what else you could do? You could multiply by y, and then you could have no quotient rule. So I think that's probably in our best interest to multiply both sides by y. So I have x plus 3 on the left, and I have 4xy plus y cubed on the right. Now, I eliminated the quotient rule on the left, but in reality, I introduced a product rule on the right. This is now a product of two variables. Do you see that? So there is give and take in doing so. It's not like I just get out of everything scot-free. There is a little bit more complication on the right because I did that. But I still think it's probably easier than we would have had to do if we worked on just the left. So we can take our derivative. What's the derivative of x? 1. What's the derivative of the 3? 0. So the derivative on the left is just 1. This piece right here is a product. So we have to use the product rule. So the product rule says I rewrite the first piece and I take the derivative of the second. What's the derivative of y? Y prime or dy dx, right? So I write dy dx. And then I add, and I'm going to take the derivative of 4x, and that is 4. And I rewrite the y. So this piece right here is the derivative of the piece in blue above. It is messier. And then I've got the y cubed. So y cubed is a chain rule. First thing I do is I pull my 3 down and make it 3y squared. But then the derivative of y is dy dx. So again, anytime I'm actually taking the derivative that involves y, which this does, I'm getting a dy dx associated with it. Okay, so this is that caveat at the end. I have to solve for dy dx. So over here, if I solve for dy dx, it looks really messy. It's not quite as bad as it looks. So anytime I have multiple of something that I'm trying to solve for, which I do, I have dy dx in 2 locations here, right? So I can't just shift things and move it and isolate this single dy dx. I got 2 dy dx's. So what I do is I move anything that doesn't have a dy dx. So this 4y, it didn't have a dy dx, so it can be booted to the other side. So that's my first step, is to get only the pieces that have the dy dx on the same side. So this is 1 minus 4y, and then everything else, namely 4x dy dx and 3y squared dy dx, they have dy dx in them, correct? So here's why we want to do that. Because they both have dy dx in them, you can factor dy dx out of those terms. So I can write this as dy dx, and then the first piece with the dy dx removed is 4x. And the second piece with dy dx removed is 3y squared. Okay, so do you see the transformation that happened? It's a little bit of algebra, but it looks a little different than what you're used to. So how many dy dx's do you have now? 1, which is really what we want. We want to be able to solve for dy dx. The only way that can happen is if I get it alone. There's only one of them there now. So what would I do now to isolate the dy dx? Somebody said it. Be bold. What do you think? Divide it. Faith, what are we going to divide by? Right, the part that's in parentheses, yeah? So we're going to divide by the 4x plus 3y squared. Now we have dy dx written on the left or the right, whichever one you really want. And I have 1 minus 4, was it minus? Yeah, 1 minus 4y over 4x plus 3y squared. Okay, so now the part that's currently on the left of my equation. If it had the ability to be simplified, like let's say everything had a y in it, or everything was had a factor of 2 in it or something, we would simplify that. But this one doesn't. All of the pieces here do not all contain something that can be simplified. So we're done. Now it's worth noting that if you decide to use the quotient rule, your answer might look slightly different at the end, but it will be equivalent. And it would be okay. I would have both versions written down on any answer key that I would be looking at, or I would follow your work along and find any errors you did along the way. So it would be all right if you decided to do this with a quotient rule. Okay, let's try another one. Same directions. It actually says y prime on all of these, or on this one. I don't know why the directions are y prime here. Probably somewhere a different book or something we've used, but that's okay. We have x squared, y squared, plus 37 equals 4x. So I don't have any quotients or anything to eliminate like I did in the last one, so we can just sort of dive right in. What's the overarching rule present in this particular term? Product. I have two pieces that are both variables multiplied. It's a product rule. Okay? So with the product rule, I rewrite the first piece, and then I need the derivative of y squared. So what's the derivative of y squared? Right. 2y dy dx. Good job, Reed. That's half of the product. Now we're going to do it the other way. What's the derivative of 2x? What's the derivative of x squared? 2x. Getting ahead of myself. And then I rewrite the y squared. You know. All right, what's the derivative of 37? Down 0. So there's nothing to write, or you can put 0 in there if you want to. And what's the derivative of 4x? 4. So this one's really nice. It actually only has one dy dx, yeah? So I don't have to worry about any factoring on this one. I'm going to shift the pieces that don't have the dy dx over. I'll clean up this a little bit. So I have 2x squared y dy dx. And I can move this as negative 2xy over to the right. Sorry, my 4 got disappeared. Let me put it there.
Y should be squared.
Thank you. Okay, any other pieces I missed? Awesome. All right, what do you see now? What did I do to solve for dy dx? Divide again, right? Seems like that's typically our last step. So we'll divide by 2x squared y. So what do you notice here that we didn't have in the last problem? Yeah, there's a 2 in everything, right? So this one actually can be reduced. Now 2 is the only piece that's in every term. Agreed? So I can't cancel out the x's or the y's. I know it's awfully tempting, and sometimes I see people do stuff like this. You can't do that because the 4 doesn't have an x in it. Remember that? Go like this if you remember. Okay, good. But they do all have a 2 in them, right? Here's the 4, here's the 2, and here's the 2. So I can actually factor a 2 out or cancel a 2 out of all of those. So this 4 will be a 2, this 2 will be a 1, and this 2 will be a 1. So this can change into 2 minus xy squared over x squared y. Okay, how are we doing? Is there anything you need clarified before I keep going? It's all good? Okay, the next one's got trig in it. So we have sine xy, and it equals x squared minus 3. Okay, so there's a sign, I get that. But do you also notice that inside of the sign, there's a product? Yeah? So we actually have a chain rule because there's a sign of something that's got more than one piece inside of it, and we've got a product inside of that chain. Kind of like some of the things that showed up on your quiz today, right? Products and chains intermixed. So we'll start with the outside. What is the derivative of sine? Cosine. And anytime we do the chain rule, we write the angle the same as it already is inside of cosine. But then we need the derivative of the angle xy, and it's a product. So we rewrite x. What's the derivative of y? dy dx. Product rule has addition between them. Then I need the derivative of x, which is 1 times y. So that's the product rule part of the derivative. On the other side, derivative x squared is 2x, and the derivative of the negative 3 is 0. Okay? So the reality is, it's really only the first step that involves any calculus. That's the calculus step right there. That doesn't necessarily mean that the algebra is clean and easy afterwards, but it is algebra, all right? Now, when I look at the next piece and I think about this in terms of algebra, this piece, the cosine xy, is being multiplied by a parenthesis with an addition in the middle of it, right? So that's the distribution rule. So I'm going to distribute the cosine xy through that next set of parentheses, the part that came from the product rule. Now, when I do that, I like to write any variables in front of cosines. That's just my thing. And I like to write dy dx's at the end. That is not a requirement. You can put them in any fashion you like. But please do understand that the dy dx is multiplied by cosine xy. The xy is inside of the cosine. Those kinds of pieces don't get to be multiplied together. So this is not xy times dy dx. It's the cosine times dy dx. Okay? On the other piece, I've just got y, cosine of xy. So again, kind of like the last problem, I only have one dy dx, so I can shift everything that doesn't have dy dx over with the 2x. So my x cosine xy dy dx will remain, and then I will have 2x minus y cosine of xy. And my last step. I think every single time so far it's been division, right? It's not always going to be division, but it has been so far. Yeah, so we're going to divide by x cosine xy. So dy dx equals 2x minus y cosine of xy divided by x cosine of xy. And again, if you look at all three terms, these are the three terms, they don't have something that's exactly the same in all three of them. So I don't get to cancel or simplify anything any further. Any questions on that one? Because the directions are about to change a little bit. Okay. Directions start out the same. Find dy dx by implicit differentiation. The last piece says evaluate the derivative at the given point. Okay. You've done this before. The interesting thing that happens in your book is that when we were doing the earlier stuff in chapter 2, it would still do this, right? It would give you the xy ordered pair, but then when you evaluated it, you really only needed to plug x in, right? Well, here you may actually need to plug y in because, like, take a look at this last problem. Does the right-hand side have only x's? No, it has x's and y's. So it's very friendly that this particular textbook publisher feels that it's useful to you to give you the x and the y. Some textbooks only give you x and they make you find y and then use it. So that's kind of a friendly step, actually. But we're going to actually need the x and the y, both of them, when we're done. Now, the part at the beginning starts out the same. We're finding dy dx. And if you take a look at the left-hand side here, what derivative rules do you see used here? What are we going to need? Yep. We're going to need product. Some of you are mouthing it. You're not like verbalizing anything. But yeah, product. What else are you going to need? We're going to need a chain rule because the y is actually a function itself that's inside of the cosine, right? So we're going to have a little bit of that going on. And then we have the cosine rule too, right? Yeah. Okay, so overarching though, it's a product. I have x times the cosine of y. So I'm going to rewrite my x. And I need the derivative of cosine y. So what is the derivative of cosine? Yeah, negative sine. Please put a parenthesis before you do that, otherwise you're actually writing down the subtraction problem, right? Parenthesis before the negative. It's the sine of y. But then I have, like Hayden said, a chain rule. The y itself is a piece that I have to take the derivative of. What's the derivative of y? It's dy dx. And then I need the other half. That is, I need the derivative of the x. Well, what's the derivative of x? 1, we like that one, times the cosine of y equals, and what's the derivative of the 1 on the right-hand side? 0. Believe it or not, it's really, once you get through the hard part, some people accidentally forget to take the derivative of the constant right. And sometimes they'll get equals 1 because you just, that's the easy part and you just are moving through it so quickly. So be careful on the constants that the derivatives really do become 0. All right, we can clean it up a little bit, so solve for dy dx. So I have negative x sine y dy dx plus the cosine of y equals 0. I need to isolate the dy dx, so I'll shift my cosine to the other side. So I have negative x sine y dy dx equals negative cosine of y. And then what will I do? Yeah, I'll divide. Divide by negative x sine y. So I have dy dx equals, and then the negatives are going to cancel, right? If you really, really wanted to change cosine over sine into cotangent, you could, but you really don't have to either. So I'm perfectly content with you leaving this as cosine of y over x sine of y. That is perfectly fine, right? But we're supposed to be evaluating this at the ordered pair 2 and pi over 3, right? Again, it's really nice because they gave us the x and the y value, and we need both of them. So the dy dx with the variables evaluated, right? Cosine of pi over 3, 2 times the sine of pi over 3. And there's that unit circle creeping back in, right? what is the cosine of pi over 3? Let's pause real quick and recognize. Cosine and sine. One of them is going to be 1/2 and the other one's square root 3 over 2, right? That's what happens at pi over 3. We just need to figure out which one's which. So do you remember? Cosine is 1/2. Yep. And again, if you need to reference your unit circle, not on a test, but in the meantime, do so. Double check yourself. This is divided then by 2. And then if the cosine is 1/2, then the sine is square root 3 over 2. They're kind of a matched pair. But y'all definitely know you can't leave it that way, right? Oh yeah, it's not going to happen. It is really nice, though, that you have the 2's canceling here. So that's actually fairly friendly. I'm still not going to have the fraction inside of the fraction business going on. So I'm going to multiply by 1 over square root of 3 so that I don't end up with a fraction inside of the fraction. So right now I have 1 over 2 square root 3. I'm not going to leave it that way either. So I mentioned this last time that when you have a radical of a variable, you can leave it in the denominator, but anytime you have a radical that you know is irrational, and square root of 3 would be one of those, we are going to rationalize it. So what would I have to do to get that square root of 3 to not be in the denominator? Yeah, I would multiply by it on the top and the bottom. So these two, they don't cancel, I didn't mean to write it that way. These two become 3. So I have square root of 3 on top, and I have that 3 times the 2, so 6 on bottom. Okay, so just like your calculator is not so good at graphing things that can't be written y equals, your calculator is also not so good at verifying for you that this is the right derivative. That's an unfortunate situation, but it is reality. Okay, I have one more problem. That's not true. I have 2 more problems. Totally lied. I just thought so. Let's see what we got. All right, this one says to find an equation of a tangent line to the graph at the given point and then to graph in the same viewing window. So the reason this question is asking you to graph is because you should recognize what this is a picture of. What is this an equation for? It's a circle. Okay, it's a circle with a funny radius. I mean, like that's going to have a square root 37 radius, which is just a little more than 6. But the center, do you know what the center is? Somebody's saying it. Center what? -2, 3. You take the opposite sign of the numbers that are being added and subtracted to the y. And then the radius is the square root of the number on the right, so square root 37. So, which is approximately 6 point something. I don't even think I wrote down an approximation, but we're pretty close. Okay, so we're going to do derivatives first, and then we're going to sketch a graph of this guy. So the derivatives for a circle are actually very friendly. I have x plus 2 quantity squared, so it's a chain rule. I'm going to bring my 2 down, rewrite the x plus 2 to the power 1, and then the derivative of x is 1. And then with the y part, I'm going to bring the 2 down. I'm going to rewrite the y minus 3 to the power 1. But then what's the derivative of y? dy dx. And the derivative of 37? 0. Now, what I need when I'm finding the equation of a tangent line is I need the line y equal mx plus b, right? I know I can find the b because I've got an ordered pair here. The m is what finding derivatives is helping me to do. So I don't necessarily have to solve this for dy dx. I could evaluate what I have just where it is and then solve the dy dx at the end. Either way is okay. So in other words, I could rewrite this as 2 times. My x value is actually 4, so this is 4 plus 2. Plus 2 times. My y value is 1, so this is 1 minus 3. dy dx equals 0. So 4 plus 2 is 6 times 2 is 12. 1 minus 3 is negative 2 times 2 is negative 4. And if I solve for dy dx, what will I get? 3, right? Move the 12, divide by negative 4. I'm going to get a 3. So my slope's 3. So equation of tangent line, y equals 3x plus b. Y is 1. X is 4. Or you can use the point slope form if you prefer it. So 1 equals 12 plus b. So what is b? Negative 11, right? Okay, so everybody okay so far? That's the finding the tangent line. So in general, these are not going to be equations that are going to be super friendly to graph. But this one's not so bad because it's a circle. Let me see if I have a slide. No, I don't. Well, I have a slide with space. I just don't have a slide with a graph. But you know what? We can fix that. Watch this. There. That's awfully tiny. That's better. All right, so we're going to put in our xy plane. I have a center, what was it? Negative 2, 3. That's here. And my radius is approximately 6. So we're a little bit more than 6 in each direction. And I'm going to connect it in theory. Wow, that's not going to work. Okay, that's more or less believable, right? You're going to sketch it and it's not going to look like a perfect circle and it's totally fine. And then we're going to graph also this line. Didn't write it down, I guess. Y equals 3x minus 11. So that's my tangent line I'm going to graph. So down here at negative 11, which is unfortunately not on my graph, but it's down there. Where am I supposed to be intersecting? 0.41. I feel like I have an error somewhere. Oh, I know what it is. So 4.1 is about here. I just have an error in my picture. And then my line looks something like this, although of course not drawn very well. Okay, so it's not very believable on my graph because I've got a lot of error in how I've sketched things. But that would be the line, y equals 3x minus 11. Okay, last question. It's actually a really quick one. What's the derivative of x squared? 2x. I realize I haven't actually addressed the issue on the directions. I promised I will. What's the derivative of y squared? 2y and then dy dx. And the derivative of 36 is 0. And if we were doing all the same thing we did before, we can very easily solve this. dy dx. We would move our 2x to the right as negative 2x, divide by negative 2y, and we would get x over y. Everybody good so far? Now the directions actually want me to find this notation. Any idea what that's asking me for? We haven't talked about this at all. This is a second derivative. So this is taking the derivative of the derivative. Now you'll notice the 2 is in a different location on top and bottom. This is literally read the second derivative of y with respect to x twice. The second derivative of y, that's why the squared's on the d, with respect to x twice, and why the squared's on the x. Now the reality is, I'm going to take the derivative down here now. So, dy dx becomes d2y dx2. The x over y is a quotient rule, so let me run through that with you really quickly. We do the denominator times the derivative of the numerator, which is 1, minus the numerator, which is x, times the derivative of the denominator, which is dy dx, over the denominator squared. What I want you to understand is that you don't get to leave it like this. It has dy dx in it, right? Y'all see it here. But what is dy dx? It's x over y. So you have to evaluate that back in for what it actually equals. So I have d2y dx2, and then I have y minus x over, times x over y squared. You can do a real quick cleanup by multiplying the top and the bottom by y to eliminate that fraction inside of a fraction. So the y multiplies here to give me y squared. The y eliminates the y right here, which is kind of the whole point, which leaves me with negative x squared. And the denominator leaves me with y cubed. And there's one more cool thing that happens. In general, this is where you stop. But on this particular problem, there's a really cool thing that happens. If x squared minus y squared is 36, what is y squared minus x squared? It's negative 36. So this is one of those rare times where there is one more piece that can simplify, and we will. d2y dx2 is negative 36 over y cubed. Crazy stuff. Thank you so much for bearing with me. This is now going to be due then on Tuesday. And we will review on Tuesday, and we will have a quiz from 2.3 to 2.5 all on Tuesday. Okay? Have a great weekend.